As any current or past geometry student knows, the father of geometry was Euclid, a Greek mathematician who lived in Alexandria, Egypt around 300 BCE. Euclid is known as the author of a singularly influential work known as Elements. You think your math book is long? Euclid's Elements is 13 volumes full of just geometry. In Elements, Euclid structured and supplemented the work of many mathematicians that came before him, such as Pythagoras, Eudoxus, Hippocrates, and others. Euclid laid it all out as a logical system of proof built up from a set of definitions, common notions, and his 5 famous postulates. 4 of these postulates are very simple and straightforward. 2 points determine a line, for example. The 5th one, however, is the seed that grows our story. This 5th mysterious postulate is known simply as the parallel postulate. You see, unlike the first 4, the 5th postulate is worded in a very convoluted way. Euclid's version states that if a line falls on 2 other lines so that the measure of the 2 interior angles on the same side of the transversal add up to less than 2 right angles, then the lines eventually intersect on that side and therefore are not parallel. Wow, that is a mouthful. Here's the simpler, more familiar version. In a plane, through any point not on a given line, only one new line can be drawn that's parallel to the original one. Many mathematicians over the centuries tried to prove the parallel postulate from the other 4, but were unable to do so. In the process, they began looking at what would happen logically if the 5th postulate were actually not true. Some of the greatest minds in the history of mathematics asked this question. People like Ibn al-Haytham, Omar Khayyam, Nasir al-Din al-Tusi, Giovanni Saccheri, János Bolyai, Karl Gauss, and Nikolai Lobachevsky. They all experimented with negating the parallel postulate, only to discover that this gave rise to entire alternative geometries. These geometries became collectively known as non-Euclidean geometries. While we'll leave the details of these different geometries for another lesson, the main difference depends on the curvature of the surface upon which the lines are constructed. It turns out that Euclid did not tell us the entire story in Elements. He merely described one possible way to look at the universe. It all depends on the context of what you're looking at. Flat surfaces behave one way, while both positively and negatively curved surfaces display very different characteristics. At first, these alternative geometries seemed a bit strange, but were soon found to be equally adept at describing the world around us. Navigating our planet requires elliptical geometry, while much of the art of M.C. Escher displays hyperbolic geometry. Albert Einstein used non-Euclidean geometry as well to describe the way that space-time becomes warped in the presence of matter as part of his general theory of relativity. The big mystery here is whether or not Euclid had any inkling of the existence of these different geometries when he wrote his mysterious postulate. We may never know the answer to this question, but it seems hard to believe that he had no idea whatsoever of their nature, being the great intellect that he was and understanding the field as thoroughly as he did. Maybe he did know and intentionally wrote the parallel postulate in such a way as to lead curious minds after him to flesh out the details. If so, he's probably quite pleased. These discoveries could never have been made without gifted, progressive thinkers who were able to suspend their preconceived notions and think outside of what they have been taught. We too must all be willing at times to put aside our preconceived notions and physical experiences and look at the larger picture, or we risk not seeing the rest of the story.